Okay, we're going to look at the first law of thermodynamics in this chapter and start by talking about thermodynamic systems. Now, the goal of this chapter is to talk about different thermodynamic processes. And in these processes, we are going to try to extract work, okay? Oops, let me get rid of these. I'm going to try to extract work from some type of thermal system, okay? Eventually, we will get work from thermal energy. And this thermal energy can come in the form of that looks like work, that's work. This thermal energy can come in the form of heat or extracted from some internal energy from a system. So look at the word thermodynamic. Thermo, talking about thermal energy being converted into work. Dynamic. Dynamics is the study of motion. So again, we are going to convert thermal energy into mechanical energy. That's a whole idea of thermodynamics. And thermodynamics became a very big branch of physics at the time that the steam engine was being developed and refined. Scientists were trying to physicists were trying to improve the efficiency of these engines and get as much work out of the system as possible. So let's talk about a thermodynamic system. We will talk about a system and how it interacts with its environment. So starting out with our thermodynamic system, the system itself is going to be some device that we're going to use to extract this energy, to get this mechanical energy out from. We'll see we can use pistons to do this. We can use steam turbines or gas turbines to do this. But basically, somehow, we are going to use an expanding gas to drive some mechanical system and get work from that. Now, the system is interacting with its surroundings, its environment, through some type of interface. This interface is a boundary. And this is a very abstract idea right here, because we can have heat coming in from the outside. We can get heat dumping to the outside. We can interact via, different pressures. But basically, the boundary allows a transfer of energy. Can be work, heat, or other forms of energy with the surrounding. Okay. Again, one of the easiest devices to extract work from the internal energy of a system would be to use a cylinder with a piston. It was the most basic type of system. And again, we are going to usually use some type of working gas within this piston. It doesn't have to be a gas. You can actually use a liquid, or you can use something else. But normally, we idealize a system using a very simple gas, such as an ideal gas, or something that approximates an ideal gas. Okay. And again, here's our boundary for this particular case. This is the movable piston that can go upward or can go downward. And it interacts with its surrounding by allowing us to transfer work out of the system. Okay. Or another boundary might be this walls or bottom, where we can add heat to this particular piston. Okay. So the boundary allows us to have an interface with some other, surrounding. Okay. The walls of a cylinder can allow heat to go in, can allow heat to go out. And if we want work to go in or out of the system, that movable piston will allow us to do that. So that's why we use a cylinder and a piston for many of these different examples. And if you think about practical cases, we see this in the real world also. Internal combustion engines still have pistons, okay? We combust a gas within there. The gas, which is in the cylinder, is allowed to expand. That moves the piston upward. The piston is attached to whatever we want to do work on, maybe a crankshaft, and that powers the whole system. Now, in thermodynamic systems, we can think about them or categorize them according to how much interaction they have with their surroundings. The least interactive system, or the system that would have no interaction, would be an isolated system. Okay, this would have absolutely no exchange of energy or mass with the outside world. Okay, good example of a system like this might be a doer, or what we call, I think it's actually a trademark. Oh gosh, I want to call it a thermistor, but it's a thermos. Couldn't think of that name. A thermos would be a good example of an isolated system. We don't allow any heat in, we don't allow any heat out. The next level of system would be a system that is closed to the exchange of energy. It's closed in respect, of mass. It doesn't allow any mass in, it doesn't allow any mass out. This is a closed system, so mass will not enter, mass will not leave. But it does allow for the exchange of energy with the outside world, okay? What would be a good example of something like this? A Stirling engine, as we'll look at in the next chapter, would be an example of this, where we have some working gas within the closed system that we allow to heat up, expand, and then we allow it to give up its heat to a cold reservoir, okay? Most systems that produce work, most engines that produce work, such as the internal combustion engine, would be considered to be an open system, okay? We have a steam engine where the boiler is boiling off water. The steam is then allowed to vent to the outside. Certainly in that typical system, we would be losing mass to the outside. We'd have to refill the boiler. Another example is an internal combustion engine, right? We need to take in the fuel-air mixture and then exhaust it to the outside, all right? Eventually, you've got to fill up that gas tank again to restore the matter which we lost as the combustion reactions converted the hydrocarbons and oxygen into carbon dioxide and water vapor, okay? So again, you can see how these different thermodynamic systems work. In the case of an isolated system, that's not going to be really of much use to us, okay? That's good for storing cold liquids for a long time. It's good for storing hot liquids for a long period of time. But in terms of a thermodynamic system where we can get work out of it, it's not going to be able to do anything. Closed systems, such as a Stirling engine. Primary loop in a nuclear reactor would be another example of a closed system. Solar hot water panels would be an example of a closed system. Here we can exchange energy, we don't exchange mass. And then finally, an open system, such as a boiler, which is open to the outside. Any non-loop system, combustion engine would be an example of that. Okay. So again, here would be one example of a thermodynamic open system, and we'll use a very simple example. This is a boiling pot of water. All right. Watching the exchange of energy, we see heat coming in from a burner or some heat source. This can be an electric heat element, it can be a gas burner. But in any case, from the outside surroundings, energy is entering into the system and it's adding energy to the water that's in the pot, raising its internal energy. Well, as the water boils, some of the mass is lost as steam, okay? Not only is it carrying heat with it in the form of latent heat of vaporization, but we're also losing some mass to the system. So certainly this is a nice example of an open system. Now, if we put a little cap on this and then we attached this to some sort of piston, we could have it actually do work. Here's a partially closed system or a closed system. Again, in a nuclear reactor, it's the heat from the fission of uranium that is then used to heat water. That water then is transferred to a secondary loop, which creates steam and drives turbines. In this particular case, we are using solar hot water. This is more popular in warmer climates where it's more efficient, where we have more sunlight. But you can clearly see that energy is allowed into the system. In this case, energy is coming in as light, okay? It's heating up a working liquid. The working liquid is then stored. And then this water can be circulated throughout a house to allow this heat out when it's needed. So in this case, energy comes in the form of light, and energy leaves the system in the form of heat. There's no net loss or gain of mass. And then our isolated system is a system that can't interact with the surroundings. So this really wouldn't be useful to create a heat engine. This would not be useful to create an engine which converts internal energy into work, okay? This thermos flask or this dewar, if you have some type of hot liquid already, it will remain warm because heat is not allowed out, heat is not allowed in. If you've got a cold liquid, same thing is true. The internal energy of this system basically remains zero because it cannot interact with its surroundings. So its temperature can't change.